Hey, Gen Chem Nation. We are talking about redox chemistry. And we've already talked about oxidation numbers. Talked about the idea of, reduction, oxidation. And we've also talked about balancing. Of redox reactions. And we've done that under acidic and under basic conditions. So these are things that should already be in our tool belt. Otherwise, look back to past videos for review. And so we are getting into now the notion of really more calculational aspects as far as reduction potentials and cell potentials. So, as far as some symbology here, reduction potentials have this type of denotion of capital E. We still have the notion of standard state. And so really what E is really signifying is the idea of potential. And then specifically talking about reduction. So we have, reduction potentials. We also have cell potentials. And so we can write it, very much in the same regard. We tend to see this idea now where we're specific with the notion of a cell, which really is just kind of this idea of a battery. So we have this notion of reduction potentials or cell potentials, and the units that we have in terms of, this general idea of potential, it's in terms of volts. And a volt is 1 joule per coulomb. So there's our volt idea. That's what we're going to be using a lot in this particular section of redox chemistry. Other units would really be looking at the amp. And the amp is 1 coulomb per second. So we have those two different ideas. We've obviously heard of both of those terms, volts, or Duracell batteries, 12-volt battery, right? And we look at amps, we look at our computers, our TV, right? We know there's a certain draw, like as far as energy is concerned. And so we're going to be relating these two units within this idea of potentials. And so the first place that we start is the standard hydrogen electrode. And so basically this is the focal point for reduction potentials. So if we think about the reduction of protons, we would have something that would look like this, that we would have a proton, let's say the proton's aqueous, and it's going to have to be reduced to hydrogen gas. So if we think about oxidation numbers, we're going from a +1 state to a 0 state. So that's a reduction. Or our gain of electrons. So if we balance that out, we would want to put, a 2 in front of the proton so our hydrogens are balanced out. And then we would also want to put 2 electrons. So there's our balanced, this reduction reaction, right? So this is basically for the reduction of protons. And that reduction potential is equal to 0 volts. So we're looking at this idea of the half reaction for the reduction of H+. And so that's what we're seeing here. And so the reduction of protons, at 25 degrees Celsius, 1 atmosphere, and 1 molar. Remember, that's, what standard state is. This particular reduction was arbitrarily set as 0. So, all other, elements / molecules, are just either easier to be reduced or not. Compared to the standard hydrogen electrode. So it's just a way of relating molecules and elements and their reduction of potential, really the ability to actually accept electrons. So as a result, we can have reduction potentials that are positive. And these are favorable processes. We could say that we could talk about it as in terms of spontaneity, right? A contributing factor to spontaneity. So we have this idea of contributing. Coming our way. We also could have the other side of the coin, which is negative. And we would say that's really now something that's more non-favorable. That idea that it's not a driving force, while above we would have a better language is, is a driving force. As far as like relations to spontaneity, Gibbs energy, right? That idea of spontaneous processes. So that's just looking specifically at the reduction side of things. And so, with redox, processes, there is always, two things though, right? Reduction and oxidation. So that means that we have two entities with the idea of potential. One in terms of, a reduction potential, in terms of E reduced. And then we also now could have this idea of an oxidation potential, right? There are two things, right? Because both of these overall give the reaction that we're looking for. And so that is the nature of cell potential. And so this is now talking about the redox process, right? The whole thing. Both that reduction side of things and that oxidation side of things. So our cell potential is equal to our reduction potential minus our oxidation potential. And so this really relies on a couple of things, and so some a really hard thing to kind of get past here that we have to understand is that the potentials for reduction can be easily looked up in tables. The problem is you won't find oxidation potentials. So this is really a problem area for a lot of students because, to be honest, this equation is taught really, two different ways, and this is one particular way to talk about it as far as reduction minus oxidation. The problem we have here is, again, the only thing that we can look up is reduction potentials. So what happens with the other side of things, the oxidation potential? For oxidation potentials, just find the opposite reduction potential and plug into EOX, or oxidation potential. What we have to understand here is that even though the reaction is in reverse from the table, the minus sign in the equation the equation that we're talking about here, this minus sign, changes sign for us. And that's just kind of an enthalpy idea. So just plug in into equation. So that's the nature of calculating these ideas of cell potentials, is we have to figure out, both of this idea of reduction and oxidation. And so we can get our idea of our reduction potential from the half reaction for reduction, and then we can get our potential for oxidation once we understand the half reaction for oxidation. Those two half reaction potentials into the equation, we can obviously get two different, values. We can get something that is positive, or we can get something that is negative. If E cell, or the cell potential, is equal to something that's positive, that is a spontaneous process. We'll come back to that notion with relationship to delta G later. This is basically also known as a galvanic battery, or voltaic battery. If you look at the small Duracells, those are voltaic batteries on their labels. If you look at the bigger ones, go into like the big flashlights and things of that nature, you'll see galvanic sometimes. Voltaic's definitely more of a current term than galvanic, but both are really meaning the same thing, that this is a positive cell potential. This is a spontaneous process. And so we have those two different terms as far as galvanic or voltaic. We could also have our E cell to be negative, and now that's non-spontaneous. And this is basically also known as an electrolytic battery. So we have, two sides of, or two opposite sides of the same coin, whether we're spontaneous and now galvanic or voltaic, or whether we're non-spontaneous and electrolytic. And so that just deals with the sign of the cell potential, whether it's positive or negative. So, with galvanic or voltaic batteries, right, these are batteries that, you basically plug in and they work. In my day, we had the boom box with the 16D batteries, and you were golden, right? You plug those in, it worked, right, until the batteries drained out, right, and you ran out of juice, basically running out of starting materials. With electrolytic batteries, now you're kind of looking more maybe on like the rechargeable side of things, if you will. Like, for instance, your car battery is a great example of an electrolytic battery, in the sense that when you start your car, it actually is using the battery as a voltaic, but you also have, within your car system, a way to recharge your battery, right? So if your alternator isn't running correctly, then you won't be able to recharge your battery as you go down the road. So these are both examples of different types of batteries that we can see. So let's do an example of this. So we want to calculate the cell potential for the following reaction. And we have here copper and zinc interacting in a redox way, reduction oxidation way. So the first step for these types of calculations of cell potentials is we still have to assign oxidation numbers to really figure out what is being reduced and what is being oxidized. And hopefully we're getting good at this. And so we see here that the copper is being reduced. See it going from the +2 oxidation state to the 0 oxidation state. So there's our reduction or gain of electrons. And then the zinc is being oxidized, going from solid zinc to now zinc +2. So we really just have the opposite transformation in terms of charge, in terms of oxidation change. So we have our copper that is gaining, our zinc that is losing electrons. So here we want to develop the half reactions. Now, half reactions are going to lead us to our reduction potential and our oxidation potential. So we can develop the half reaction for reduction. It's a pretty simplistic one with the copper +2 going to copper 0, or copper in that solid state. It must be gaining 2 electrons. right? There's no other elements here. It's just really copper. So we're just looking at that change in charge. So we would need to balance out the charge with 0 and 0. And so there is our charge balanced half reaction for reduction. And we can do the same thing for the oxidation side of the coin, where if we're going from zinc solid to zinc plus 2, well, we'd have to be losing 2 electrons. So those are the two balanced reactions. And so here is where we need to then look up the reduction potential. Right, we need to look up the oxidation potential. So what does that mean? Means we need to go to tables. Such as what we see here. Such as what we have here. So we need to look up these values for the copper, going to copper solid, and we need to look up the value for the zinc, going to zinc plus 2. Now, when we look those up, we find that we can see both of them here. So we have our copper, going from copper plus 2 to copper 0. And notice that we have a potential there of 0.34 volts. And if we go down to our table at the bottom, we see the zinc. Now notice the zinc is written in the opposite notation. Here is our potential for reduction, while here is our potential for oxidation. So once we find the reactions, just plug in the values at the appropriate spot. Meaning, for reduction, half reaction, plug in its reduction potential. And for the oxidation half reaction plug in its reduction potential. Remember, equation does all the work in terms of making sure signs are right and everything else. So that means our reduction potential above would be equal to the 0.34 volts. And our oxidation potential that we're going to plug in is going to be equal to a negative 0.76 volts. So now we can substitute the values into our cell potential. Our cell potential would be equal to then the positive 0.34 volts that we had above minus the negative 0.76 volts that we had for our oxidation side of things. And remember that our minus sign is doing the sign change in terms of substituting a reduction potential in for an oxidation potential. So that means we have, at the end of the day here, our cell potential is equal to 0.34 volts minus a negative 0.76 volts. That obviously changes the sign, and we end up with a cell potential of 1.10 volts for this particular copper zinc style battery. Now let's look at cell diagrams. Cell diagrams are basically a visual representation of the components of a battery. So this is what we can basically put together in a lab. So when we think about cell diagrams, we have to have a couple of different things. We have to have, one, we have to have our anode and our cathode. these are just different sites of reduction or actual oxidation. So if we look at the anode and the anode and the cathode are simply what we call electrodes. And electrodes allow for the conductance or transfer of electrons. Electrodes have to be metals. So when we look at cell diagrams and we start to actually put the battery together, right, we have to realize that there's two half reactions, the anode and the cathode, the site of oxidation and the site of actual reduction. So the anode is the electrode that's basically undergoing an oxidation process. And then we have the cathode, which is the electrode that's undergoing the reduction process. So those are the two pieces, right? The anode and the cathode. And you could almost look at it more like this, that the anode is the half reaction for oxidation, while the cathode is the half reaction for reduction. So we could write our equation a little bit differently in terms of the cell potential is equal to the reduction minus the oxidation, or we could say that the cell potential is equal to the cathode potential minus the anode potential. It's really kind of the same thing. So cell diagrams, we have this idea of the anode and the cathode. These are the metals that are allowing for transference of electrons, and if the metal is part of the reduction oxidation scheme, well, then that's just the actual anode or cathode. If there isn't a metal used, in either the reduction or oxidation, then an inert electrode must be used. And our inert electrodes that we use are platinum or palladium. These basically they don't affect cell potential, and merely serve as a conveyance of electrons to convey those electrons from oxidation to reduction in basically purely aqueous and or gaseous redox processes. And we'll reinforce that idea later. So, as far as our base cell diagram or base voltaic, diagram, we have, a way to represent this would be two beakers. Where we have an anode side of things and a cathode side of things. So we have here just the basic setup. Sorry for my cartoon. On the left side, we have our anode, and that's the metal that's undergoing the oxidation. So if we think about it, the metal is going from this neutral charge as a solid to this metallic in solution. So we're going from the solid metal to aqueous, and so we're losing electrons. So you can envision those coming up, basically a copper wire. Or just a wire in general to allow for conductance of electrons. Tend to use copper. So on the left side, we have the anode. And there's our oxidation. Those electrons can come all the way over to then the site of reduction. So this is basically the cathode, or the metal that's undergoing the reduction. So we would have our metal that's positive in solution being attracted to that negative source and deposited. So our cathode is that site of reduction. What monitors the whole process is the voltmeter, or the voltmeter. And so that's where we get our cell potential, if you will. But there's one missing component that we need, and that's what's known as a salt bridge. And with the salt bridge, this is just a way to actually communicate charge. It's not something that's open to the environment, so it's closed. But within, we basically have a electrolytic solution. And so the electrolytic solution allows for charge to be communicated. Kind of like in the old days, we would have two cups tied by a string, and we could hear the vibrations from one side to the other. Same thing here with this idea of charge. The salt bridge is super important for that transfer of electrons, because it actually conveys the difference in charge that we find from one side to the actual other. So those are the different base components of the voltaic cell. We have our anode, we have our cathode, we have our salt bridge, and we have our voltmeter, right? Everything's connected by wires, and then we have the two solutions. So let's kind of look through the example of what we were calculating earlier as far as this zinc, copper style battery that we found out that its cell potential is 1.10 volts. And so what we do to represent that is basically we have two beakers. Right, so we can have beaker 2 and beaker 1. And they have a solution within each one. We have two electrodes that are placed into each vat. And so the electrode is just a place for electrons to be actually transmitted. And they are attached to one another via a copper wire, and we have our voltmeter that's above, that's connecting the two. On the left side, we have what's called our anode. This is the site of oxidation. So if we look at our above reaction, we would have the zinc here. The zinc is going from zinc solid to zinc plus 2. And those electrons are headed over across the actual copper wire, right, via conductance. On the other side, we have what's known as the cathode. And that would be the site of reduction. So a reduction from that reaction above was the copper plus 2 going to produce copper solid. That's actually on the cathode side of the reaction. Between the two of them, we have a salt bridge. And the salt bridge just allows for communication of charge. And that allows electrons to flow all the way across and down to produce then a voltage of 1.10 volts for this particular type of battery that we're describing. So there's just these couple different pieces that we need to now kind of define within it. Meaning the electrodes. There is, the anode, which is basically the metal that undergoes, the oxidation. Process. And our above example, that's the actual zinc. The anode loses mass as this reaction continues. So more of the zinc is turning into zinc plus 2. Zinc plus 2 is aqueous, right? It's in solution. So it's actually really kind of dissolving. So we have the anode electrode, which is that metal that's undergoing oxidation. And then we have the counter to that, which is then our cathode, which is the site of the reduction. And so this is the metal that undergoes, and we should say maybe, you know, charged metal that undergoes a reduction process. In our example here, that is the copper. The cathode actually gains mass. So with these two reactions happening, one at the anode, one at the cathode, these two half reactions happening, we're talking about, you know, a process of something losing moles or mole transfer, in terms of the solid going to something aqueous, or the opposite process. So with the anode, you're actually losing moles of that electrode, and so you're basically seeing it dissolve or lose mass. In the cathode sense, you're actually gaining moles, so you're actually seeing metal depositing, I suppose, and then also that gain of mass. So that's the anode and the cathode side of the electrodes. And basically for this kind of definition, we need a metal electrode to allow for conductance of electrons. So that's that important piece there as well. The idea of metal and metal, that's required here. The zinc metal and the copper metal that are required for those electrodes to allow for conductance or electrons to be transported from one side to the actual other. Just to kind of represent that more in real time, check out the demo here of the copper zinc battery. You know, here is the real cell diagram. So basically representing what we have just earlier in terms of a cartoon field, now actually doing the experiment. Take a look.
This is a Voltaic cell. Notice we don't have any battery, any power source attached here, because this is the power source. This is a battery. This is what a battery is made of. At the moment, it's not generating electricity, and why not? We'll get to just now. But let's just first look at its components. Here we have an electrode made of copper, inside a solution of copper ions. Here we have an electrode made of zinc, inside a solution of zinc ions. They are connected via these crocodile clips to a multimeter set as a voltmeter, which is not reading anything at the moment, because at the moment they are not generating a potential difference across them. There we can see the completion of that circuit there. Once this is working, we will see that it's working by the fact that a potential difference will be registered on this voltmeter. So why isn't it working yet? The problem is we don't have a complete circuit. Notice that in between the two electrodes and the solutions, there's a gap. And so we know that with electricity, you have to have a complete circuit in order for electricity to flow. So we're going to complete that circuit with an ion bridge. An ion bridge is a solution which bridges across the two half cells of the Voltaic cell. And notice as we put it in, the reading registers on the voltmeter. Here we have an ionic substance inside a U-shaped tube, and that's allowing the conduction of electricity through between the two half cells.
Now there's another way to represent cell diagrams, which is known as cell shorthand. And basically, cell shorthand is, you know, as the name implies, a shorthand notation of the actual cell diagram. So if we go to our example that we were looking at earlier as far as the copper zinc battery or cell, right, that we actually drew, you know, a diagram for that as far as showing, you know, what is being oxidized and what is being reduced, right? Remember our copper here was undergoing the oxidation. I apologize. The reduction. And the zinc was then undergoing the actual oxidation. So that meant that, you know, we had certain anodes and cathodes, and we ended up with, you know, as far as drawing it very quickly, you know, something that looked like this. Where we had our zinc going to zinc plus 2, and that was our anode. Or oxidation, and we had, you know, these connected, the electrodes. On the other side we had the copper being reduced. So there's where our cathode is for the reduction. And we had this, you know, voltmeter right, giving us an idea of voltage. And then lastly, we had the salt bridge. So that's, you know, this idea of cell shorthand. Quick review there. Maybe not completely necessary for all, but the idea of cell shorthand is it really mimics the idea of the cell. Or the cell diagram. So we would write it, you know, much in this way, where we would show zinc as a solid. That is our anode, right? That's where oxidation is going to occur. And then we have a vertical line. And the vertical line is really indicating a phase change. Here, going from the solid to the aqueous state, because on the other side of the arrow, or I'm sorry, the vertical line, we now have the zinc that's aqueous, and we have the +2 charge. We would want to put a concentration this is very important. Here talking about standard state as far as the 1 molar idea. So we often put in those concentrations or pressures. So now we've taken care of essentially the anode side of things. Now we're going to the cathode side of the equation. And we need to represent that by something new here, and this is called our salt bridge. So just like we had above, as far as our anode and cathode, right? They're both actually separated from one another as far as the solutions are concerned. And so what connects them is really that salt bridge. So really showing the dividing line between one side of the battery and the other side of the battery. And so now we just kind of go backwards within, now we're really in like the beaker. We have another vertical line for our phase change. Here we're going from the aqueous to the solid state, and then we have our copper solid, and that is our electrode, specifically the cathode. Or that site of reduction. So the cell shorthand motif is really just a shorthand of the actual cell diagram. Instead of drawing all of those things, we can just minimalize it as we see here. So that's the notion of cell shorthand. So let's do an example of now all three of these recent ideas as far as calculate cell potential, this idea of the cell diagram, and this idea of then cell shorthand. So here we have our example. So we're just saying, for the following redox reaction, and so here we have manganate plus 8 protons plus 5 silver in the solid state. Produces manganese plus 2. That's aqueous plus 4 H2Os and 5 silver ions. So there is our redox reaction, and we want to calculate the cell potential. For part B, we want to draw a cell diagram. And for part C, we want to represent in cell shorthand. So there's 3 pieces to this question, bringing in the past 3 components that we've talked about. So for part A, right, where we want to calculate the cell potential, right, we need those steps. As far as 1, we need to assign oxidation numbers. 2, we get the half reactions for the reduction and oxidation. And then 3, we look up potentials and we substitute them into our expression as far as our reduction minus our oxidation. So those are the 3 things that we need to do. So if we go to the very top, right, we can start to then assign oxidation numbers. If we look at our manganese here would be in the +7 state. Our oxygen is in the -2, but there's a total of 4, so that's -8. So that's why we have the manganese in the +7. The hydrogen is in that +1 oxidation state, oxidation number, and the magnesium is 0. We go to the product side, the manganese is +2 now, and so there is our reduction. The manganese and manganate on the starting material side is in the +7 oxidation state, or oxidation has that oxidation number, and now it's +2, so there's a gain of electrons. If we look at H2O, right, there's nothing changing there as far as the elements. The hydrogen is still +1, like on the starting material side, and the oxygen is still -2, like on the starting material side as well. And so that means the silver must be the other player, and it actually is. The silver is oxidizing. It's going from the 0 state there to the +1 state. So with that step 1, we know now that the manganese is being reduced, and that's because of the manganate going to manganese +2. They're both aqueous. What we're looking at going from the +7 manganese to the +2 manganese, and so there is our reduction or gain of electrons, and the silver is being oxidized. So we have our silver in that solid state going to silver +1. That's aqueous. Change of oxidation number going from that 0 state to that +1 state. And so that is our oxidation, or loss of those electrons. So that's really step one, right? Assigning oxidation numbers, figuring out what's being reduced and what's being oxidized. And then we go to step two, which is now, what are the half reactions? Right, we need those balanced half reactions so that we can look those reactions up in our table and then assign a value. So for the manganate, and I'm just going to go somewhat quickly here, since we should be practicing these things, and hopefully are good now. If we have the manganate going to manganese +2, you know, our manganese is already balanced, so we would add our 4 H2Os to balance out the oxygens. We would add our 8 protons to balance out the hydrogen. And then with the charge, we would add 5 electrons. And so there is our balanced half reaction for reduction. You may need to review balancing if that was difficult for you. So then we go to the half reaction for oxidation. And so now we're looking at the silver going to silver +1. And so this is a much easier one to balance. There's no oxygen or hydrogen, and the silver is already balanced. So we just have to balance out our electrons by adding one of those electrons to the product side. Now that we got both half reactions, we can look up the values. Or, you know, look up the potentials. So if we add that document, you know, we were looking for, you know, 2 reactions. We were looking for that idea of the 5 electrons plus the 8 protons plus the manganate produces the manganese +2 and the 4 H2Os. So we're looking for that potential for reduction. And then we're also looking up the idea of the silver going to silver +1. Now, here we're also looking for that potential of reduction from the table. We just want to make sure that we plug this value in for our oxidation potential, right, in terms of that equation of the cell reduction minus oxidation. So we're just going to be plugging that value directly in. So if we go to our table and expand, there is our one reaction at the very top here. We have the manganate going to manganese plus 2, and that is 1.51 volts. And if we go down a little ways, we can see the silver as well. Right here. And there is our value of 0.80. So those are the two values of reduction potential. And now we're just plugging them into the appropriate spot as far as this is getting plugged into our oxidation as far as the 0.8, and the 1.51 is getting put into the reduction side of things. So that means in terms of solving for our cell potential, we now know our values over here for the reduction and the oxidation side of things. Granted, they're both reduction potential. We just want to plug them into the appropriate spot and let the equation do the work. And so our cell would be equal to the 1.51 volts minus the 0.80 volts, and we end up with a potential of 0.71 volts for this particular battery, particular electrochemical cell. For step B, now we're looking at that cell diagram representation. So basically we have to still, we have to represent both processes that are occurring in terms of, not necessarily the count or the number, but just the different molecules and conditions that are part of both sides of the battery. Right, so that's our, reduction side of the game. And we have our oxidation side of the story, which is the silver. So that means we just got to represent these on the appropriate side of the cell diagram as far as the anode side or the cathode side. So if we have our two solutions, right, for our batteries, we have our two electrodes that are in the solutions. Right, connected by that voltmeter, which gives us the cell potential for the conditions we have. And then we also have our salt bridge. So these are all the necessary components, if you will, for the experiment or putting the battery together. And remember, these are separate. There's a cap on these, just a communication of charge. So we have the anode on the left. We have our cathode on the right. And so now we're just putting the different components from above on either side. So let's start with the oxidation. And the oxidation, we have the silver. Silver is metallic, so it can be the electrode or the anode. And it is producing silver plus 1 in solution. And so those electrons are being transferred up and across to then the reduction side of things. To now the reduction. Now, if we look above, we don't have a metal. So we're going to use that inert electrode that we talked about earlier. Since there's no metal part of the actual reduction that's occurring. So the reduction is the manganate. That's aqueous. It's getting electrons and then turning into manganese plus 2. The other thing that we need to write here is that we are under acidic conditions, so that H plus is there as well. So we're writing in all the components of those two half reactions. And the base components are the electrodes, the voltmeter, the salt bridge, and then it's just putting in the half reactions, that represent each side. And so our reading above would be equal to that 0.71 volts as far as our voltmeter is concerned. So that is the part B of this process, the actual cell diagram. Part C is looking at now the cell shorthand of this reaction. So it's really taking what we just did with the cell diagram and now compressing it within cell shorthand. So, we would start from left to right, saying that I have solid silver, then that's turning into silver plus 1, that's aqueous. We have here our anode, right? We're talking about our oxidation side of the half reactions. And we see we have our phase change, right, with that vertical line. We would want to put in the concentration since we're at standard state. So remember, that's that idea of the 1 molar. We have our salt bridge. Breaking up the two solutions. And now on the right, we have to write basically all of those quantities that we have there. So we have the protons that are 1 molar. We have the manganate. That's also 1 molar. We have the manganese plus 2. One molar, and then we have our vertical line to indicate the change of phase right now going to the solid state, and so that would be then our platinum, our inert electrode, but that is our cathode or site of reduction. So that is the cell shorthand for this particular process. Again, just a shortened version of what we see above.